in this session let us solve some problems based on the concepts which we have developed for uniform plane wave. So, we will try to find out, for examples, the electric and magnetic field or the phase velocity of the wave or the polarization of the wave in this session. So, let us consider a problem here. A uniform plane wave at frequency of 300 megahertz travels in vacuum along plus y direction. The electric field of the wave at some instant is given as E equal to 3x plus 5z, where x cap and z cap are the unit vectors. Find the phase constant of the wave and also the vector magnetic field. So, in this problem the electric field, vector electric field is given at some instant of time, and we are asked to find out the phase constant of the wave and also the vector magnetic field. Now, since the wave is travelling in vacuum, the wave travels with velocity of light in vacuum, that is given as 1 upon square root mu epsilon. So, we get the velocity of the wave v, that is equal to 1 upon square root mu 0 epsilon 0, where mu 0 and epsilon 0 are permeability and permittivity of the medium respectively, and that is equal to 3 into 10 to the power 8 meters per second. The phase constant, as we know, is given of the wave, which is beta, that is equal to omega square root mu 0 epsilon 0. So, that will be equal to, the frequency is 300 megahertz. So, this is 300 into 10 to the power 6 into 2 pi divided by this quantity, which is 3 into 10 to the power 8 meters per second. So, from here we get the phase constant of the wave, which is 2 pi radians per meter. Now, since the wave is travelling in y direction, and for uniform plane wave the electric and magnetic fields lie in a plane perpendicular to direction of wave propagation, the E and H both vectors must lie in a plane which is perpendicular to the direction of wave propagation, which is plus y direction. So, that means the electric and magnetic field vectors both lie in the x z plane. Okay, x z plane is the plane which is perpendicular to the plus y axis. The E which is given here has components in the x and z direction. So, this vector lies in the x z plane. The magnetic field vector also would lie in the x z plane. So, let us assume that the magnetic field vector H, now which lies in the x z plane, is given as A x cap plus B y z cap. So, now we have electric and magnetic field vectors which lie in the x z plane, and we know from the property of the uniform plane wave that the electric and magnetic field vectors also must be perpendicular to each other, and the ratio of the amplitude of electric and magnetic field is equal to the intrinsic impedance of the medium. So, we can essentially make use of that property to say that E dot H, that is equal to 0, and also for uniform plane wave mod of E divided by mod of H, that is equal to the intrinsic impedance of the medium, and in this case the medium is vacuum. So, this is equal to eta 0, which is nothing but equal to 120 pi for the vacuum. So, now we can write down the electric field is given, which is 3 x cap plus 5 z cap. So, I can write here and h is given by this. So, we can write the dot product which is E dot h that is equal to 3a plus 5b that is equal to 0. So, this is one equation. The second equation which we get is the magnitude of the magnetic field is mod of E divided by eta 0. From here we get mod of H equal to square root of A square plus B square that is equal to mod of E divided by eta naught, and that is equal to square root of mod of E, which is 3 square plus 5 square. So, this is 9 plus 25 divided by 120 pi. So, this is equal to the mod of H is equal to 15.48 into 10 to the power minus 3 amperes per meter. Now, knowing this quantity, this is the second equation which you have, which relates A and B. So, from these two equations one can solve for A and B. So, we get A is equal to plus minus 5 upon square root 120 pi, and B is equal to minus plus 3 upon square root 120 pi. So, the magnetic field vector H now H is equal to plus minus 5 x cap minus 3 z cap upon square root 120 pi. So, what we did first, we took the electric field, argued that for uniform plane wave the dot product of the electric and magnetic field is 0. So, we assume the magnetic field which lies in the xz plane, which has to be perpendicular to direction of wave propagation, which is plus y direction. Find out the dot product of E and H, that should be equal to 0 because E and H should be perpendicular to each other for uniform plane wave, and also the magnitude of the magnetic field is equal to the magnitude of electric field divided by the intrinsic impedance of the medium, and then solving these two equations essentially we get the vector magnetic field. So, this is one of the simple problems where the electric field was given and we were asked to find out what is the corresponding magnetic field of the wave. Let us take another problem which is related to the polarization of the electromagnetic wave. So, let us say that we have to generate a left-handed elliptically polarized wave. So, the problem is as follows: a left-handed elliptically polarized wave is to be generated using x and y polarized waves. The tilt angle and the axial ratio of the ellipse of polarization is 30 degrees and 3 respectively. Find the amplitude and phase of the x and y polarized waves. Assume the wave to be propagating in the positive z direction. So, this problem again is a very straightforward problem. essentially what we are saying is that if you have two orthogonal polarization which are x and y, in what proportion they should be combined together to generate an elliptically polarized wave which is left handed sense of rotation and has a tilt angle of 30 degrees and axial ratio of 3. So, for this problem, if we go to the notation which we have used in our analysis, essentially we are given the quantities, the tau, the tilt angle, that is equal to 30 degrees, so equal to pi by 6 radians, and epsilon which we have defined as cot inverse of axial ratio, and in this case the axial ratio is 3 with a sense of rotation which is left handed, and we have used the convention that the sense of rotation left handed means positive sign. So, axial ratio for left handed elliptically polarized wave is plus 3, that is equal to 18.4 degrees. Now, using the expression which you have got for conversion from the ellipse parameter to the electrical parameter, which is the ratio of the amplitude of x and y component and the phase difference between them, we can get these quantities what is called gamma and phi. So, we have defined this quantity gamma. So, we know gamma which is equal to tan inverse of E y upon E x, and the angle phi is equal to angle E y minus angle E x. And knowing the transformation relation between these parameters, we get cos of 2 gamma which is equal to cos of 2 epsilon cos of 2 tau. Substituting for epsilon equal to 18.4 degrees and tau 30 degrees, we get cos of 2 gamma, and from there we can solve for gamma to get gamma is equal to 33.2 degrees. So, the ratio E2 or Ey upon Ex, that is equal to tan of gamma, that which is equal to 0.65. The phase angle phi can be obtained by using this relation, that tan phi is equal to tan of 2 epsilon divided by sine of 2 tau, that is equal to 0.8658, which gives angle phi that is equal to 40.88 degrees. So, what essentially we get now, that if I take a coordinate system which is, let us say this is x, this is y, and now if I go put my right hand rule, the x to y, if I do then z must come like this. So, this is the direction which is z. So, if I take the ratio of the electric fields in the x and y direction, which is 0.65, and if we excite these fields with a Ey component leading the x component by 40.88 degrees, then we will generate an elliptically polarized wave with a axial ratio of 30 degrees, axial ratio of 3 and tilt angle of 30 degrees. So, this will generate essentially a wave which will look something like this. This to this ratio, if we calculate this maximum. So, if I take this is equal to 1, this will be equal to 0.65. So, we get from here the E x component, which is, let us say, amplitude 1 cosine of omega t. So, E y component will be 0.65 cosine of omega t plus 40.88 degrees. So, by exciting these two fields simultaneously, the superposition of these two would generate a wave which will give the elliptically polarized wave of left handed sense, and since the wave is going in this direction, the rotation which is like this will be the right handed rotation. We are seeing in this direction. So, the opposite to that will give the wave which will be the left handed polarized wave. The next problem which we can now take is generation of a linearly polarized wave by a combination of two circularly polarized waves. While discussing the polarization, we have seen that a arbitrary state of polarization can be generated by superposition of two orthogonally polarized waves. In the analysis, we took two polarization which were x and y oriented polarizations, and they were orthogonal to each other, and then we showed that by combination of these two, essentially we can generate a general elliptically polarized wave. So, by eliminating the time parameter, essentially we got the equation of ellipse, representing that the electric field vector would draw a shape which will be an ellipse. One can ask a question, if I have to now generate a state of polarization by using some other orthogonal state or a pair of orthogonal states, how would I proceed? An immediate thing which can come to your mind is that if you have two circularly polarized antennas, so if I have two circularly polarized wave with opposite sense, then how do I generate an arbitrary state of polarization? So, let us take a problem here. Show that a linear polarization can be generated by superposition of two circularly polarized waves. Explain how a linearly polarized wave with a tilt angle of pi by 3 can be generated by two circularly polarized waves. So, essentially now we want to represent a linearly polarized wave in combination of two circularly polarized waves. Now, in this case, first the circularly polarized wave is given to you, or two circularly polarized waves are given to you of opposite sense of polarization, and now we want to find out, when I combine this, how a linearly polarized wave will be generated. So, as we did earlier, when we were writing the electric field in terms of x and y components, we represented the field in two components which had x and y. Precisely the same thing I can do. I can take the electric field and represent in the two components which are now left and right handed polarized waves. So, for that, first we have to define what are called the unit vectors corresponding to left and right handed polarized waves. So, let us say that the wave, we take a coordinate system which is, let us say, like that. So, this is x, this is y, and this is z, and assume that the wave is travelling in positive z direction. So, a unit left handed polarized wave would represent a vector whose amplitude remains 1 and it rotates in the left handed sense. So, since the wave is coming out of the paper this will represent, this rotation will represent the left handed rotation. So, I have a electric field which is now rotating in the clockwise direction, which will represent a left handed polarized wave. Similarly, if I consider a wave of unit amplitude whose vector is rotating in the anti-clockwise direction, that will represent a circularly polarized wave with unit amplitude with right handed sense. So, this is the right handed circularly polarized wave and this is the left handed circularly polarized wave. So, if I take the amplitude of this circle, the radius of this circle as 1, then that represents a unit left handed polarized wave and this would represent a unit amplitude right handed polarized wave. So, this one then I can denote as a unit vector for circularly polarized wave. So, let me call that as r cap and this one let us call as L cap. Now, we know that a left handed polarized wave can be generated by two unit amplitude x and y polarized wave with a phase difference between E y and A x of plus 90 degrees, and a right handed polarized wave can be generated by combination of two unit vectors x and y with E y lagging by 90 degrees with respect to E x. So, in this case, as we know that if I consider E x equal to 1 and E y is equal to 1 angle plus pi by 2, we will generate a left handed circularly polarized wave of unit amplitude. Similarly, for right handed, if we take E x is equal to 1 and E y is equal to 1 angle minus pi by 2, we generate a unit amplitude right handed circularly polarized waves. So, that means this L vector unit vector can be represented as x plus 90 degree phase shift into y. So, we get here the L unit vector we can write as the unit vector x plus j to unit vector y. Similarly, for the right handed case, we get r unit vector that is equal to x minus j into y. So, now essentially we represented the unit right handed and left handed vectors in terms of the unit x and y vectors. By solving these two, essentially we can get now the x unit vector, which is L plus r upon 2, and y unit vector that is equal to L minus r upon 2j. Now, if we consider the electric field, we can represent the electric field either by the unit vector which are r and L, or we can represent the unit vector in terms of x and y. So, any electric field now can be represented as E x unit vector x plus E y unit vector y, or this is equivalently represented by the unit vectors L and r. So, let us say the amplitude for that is E L and the amplitude for the right handed component is E r unit vector r. Substituting now for x and y from here, essentially this is equal to E x x component, which is L plus r upon 2 plus E y L minus R upon 2j. So, separating the component corresponding to L and R, essentially we get E L is E x minus j E y upon 2 and E r equal to E x plus j E y upon 2. Now, we want to represent, the problem is we want to represent a linearly polarized wave by the superposition of the two circularly polarized waves. So, essentially the field, electric field which we are representing here, this field is linearly polarized, and we know that the linearly polarized wave is generated when E x and E y are in phase. There is no phase difference between E x and E y, that gives you a polarization which is linear polarization. So, without losing generality, we can take E x and E y to be real, and then one can write this as half square root of this amplitude E x square plus E y square and angle will be tan inverse of this minus of E y upon E x. Similarly, this amplitude would be half square root of E x square plus E y square angle tan inverse of E y upon E x. Now, this quantity, if you note here, tan inverse E y upon E x, that is the quantity which gives the inclination of the line which the linearly polarized wave draws. So, if I consider a xy plane, this is x, this is y, a line linearly polarized wave will look like that, and this angle would be nothing but tan inverse of E y upon E x. So, what we see from here is that the tilt angle for the linearly polarized wave will be nothing but the phase of this component E r, or negative of the phase which is this quantity. So, so what that means essentially is that the tilt angle tau is equal to the angle of E L, which is equal to minus angle of E r, and for linearly polarized wave these two quantities are same. So, the magnitude of E L and E r should be equal. So, and tilt angle is this, and mod E L should be equal to mod E r. So, what that means is, if we consider the two circularly polarized wave of left and right handed, and if their amplitudes are same, and if they have a phase, then the tilt angle will correspond to the phase of the left handed polarized wave, and the right handed polarized wave will be having the negative phase. Now, what is the meaning of phase for a vector which is rotating in the right handed or a left handed sense? So, if we consider now a left handed wave, a rotation of the vector in the direction of rotation, that will correspond to the positive angle, whereas if I take the rotation which is up, or angle which is opposite to the rotation of the vector, then that angle will be considered as a negative angle. So, what essentially that means is that some instant of time you launch the wave and they are rotating in the opposite directions, they will meet in the direction which will correspond to this angle, which is Ey upon Ex. So, essentially what we have, if we take the two waves, one is left handed and right handed, let us say this is left handed, this is right handed, and if I consider now a vector at some instant of time which is like this and like that. So, if I consider this as some difference direction, at that instant of time the two vectors were like this. Now, this vector will rotate by an angle and this vector also will rotate by an angle. So, when this rotate, so this angle if we take to start with as 2 tau, the two vectors will meet halfway. So, that will give me the direction of the resultant vector, which will be at an angle tau, and that time the two vectors will align to give you the maximum field. So, if these two are equal and if we start with the vector position which is like this, so the difference between the two vectors is 2 tau, then you will get a linearly polarized wave with an angle tau. So, this angle is tau. So, for generation of a linearly polarized wave by combination of two circularly polarized wave, essentially is that you should have two circularly polarized wave which have equal magnitude, and then at the instant of time when these two waves start propagating, their vectors should be oriented such that the angle between these two vectors is equal to 2 tau, and then they will meet halfway. So, you will get a linear polarization which is will be inclined at an angle of tau. One can verify this, that when these two vectors are, these two amplitudes are equal, we will always get a linearly polarized wave. So, consider now situation like this. This is your one vector which is rotating, and there is another vector which rotates in the opposite direction. So, this is my left handed, and you have another vector which is of same amplitude. Just for the clarity reason, let us put this little inside this dotted line. This is the vector which is rotating opposite direction. So, the two vectors meet, this is the direction which is x. So, these two vectors meet in this direction to get a double value. This angle is tau. Now, since these two vectors are going to make always equal angle with respect to this line, as they rotate, this vector will rotate this way, this vector will rotate that way. The component of the vector which is perpendicular to this line will be of equal magnitude and in opposite direction. So, it will always cancel out, and as the vector rotate, the component which is in the direction of this line will vary. So, when the two vectors are in this direction, you get a maximum value which is this. When the two vectors are, let us say, in this direction, one is this, other one is that, the resultant of these two vectors again would lie corresponding to this. So, it will become like that. So, the value will be this, and when the two vectors become perpendicular to each other, that time they will cancel and the amplitude will go to 0. And when the vector rotate now further, essentially the point will move like that. After half cycle, the two vectors will come exactly in the opposite direction here, they will again add, and you will get an amplitude which is double. So, you will get a polarization of the wave which essentially will draw like that. So, this amplitude now will be double of the amplitude of the individual circularly polarized waves. So, this problem essentially explains how a linear polarization can be generated by two orthogonal states which are two circularly polarized waves. The concept can be extended now to any other polarization. The analysis would be exactly on the similar lines. So, you can write down the Ex, Ey, and you can write down El and Er, equate the components, and then from there you can find out the relation between the El and Er. Let us take now a problem on the dielectric and conducting property of the material. So, here is the problem. A material has dielectric constant of 25 and conductivity of 2 into 10 to the power 6 moles per meter. What is the frequency above which the material cannot behave like a good conductor? If a plane wave of 10 megahertz is incident on the material, effectively up to what depth the wave can penetrate the material, and what will be the wavelength of the wave inside the material. So, now in this case we are talking about a composite material which is neither ideal conductor nor ideal dielectric, but the conductivity is large here. So, this is more like a metal, but still we want to find out when the material can be treated like a dielectric and when the material can be treated like a good conductor. So, as we have seen that this is decided essentially by the contribution which the material gets from the conduction current and from the displacement current. So, we say the material is a good conductor. So, for a good conductor, we should have sigma much greater compared to omega epsilon 0 into epsilon r. So, let us say that this condition is much greater, means if this quantity is 10 times this quantity, just a arbitrary number, then we say the material will behave like a good conductor. So, let us say that the sigma should be greater than or equal to 10 times omega epsilon 0 into epsilon r. From here then I can find the frequency which is omega, that is equal to sigma upon 10 times epsilon 0 epsilon r. So, if the frequency is less than this, then the material will behave like a good conductor. If the frequency is more than this, then we will say it is no more a good conductor. So, I can substitute now the values for sigma and epsilon r given here. Sigma is 2 into 10 to the power 6 moles per meter, and the dielectric constant which is epsilon r, that is 25. So, you can write here 2 into 10 to the power 6 divided by 10 into epsilon 0, which is 1 upon 36 pi into 10 to the power minus 9 multiplied by 25, which is dielectric constant. Solving this, essentially we get a frequency, so omega which is equal to 2 pi into f. We get a frequency f which is 1.44 into 10 to the power 14 hertz. So, what that means is that when the frequency is about 10 to the power 14 hertz, the material will stop behaving like a conductor, good conductor, and this frequency, if you recall, is the frequency which is of the visible light somewhere here. So, that means by the time we reach to the visible light frequencies, the material which would have the conductivity of 2 into 10 to the power 6 and that dielectric constant would no longer would no longer work like a conductor, they will start behaving more like dielectric. Now, the second thing which you have to find out in this problem is the effective depth up to which the wave will propagate, and that we know is essentially given by what is called the skin depth. So, we get the skin depth, this delta, that is equal to 1 upon square root pi f mu 0 into sigma. So, substituting now for these quantities, which is delta is equal to, which is 1 upon square root pi, the frequency is 10 megahertz, which is 10 to the power 7 hertz, 7 into mu 0, which is 4 pi 10 to the power minus 7 into sigma, which is conductivity, which is 2 into 10 to the power 6. So, substituting and solving this now, we get the skin depth, which is 112.54 micrometer. And recall, the skin depth essentially is the distance over which the wave amplitude reduces to 1 over E of its initial value. So, in this material, over a distance of 112.5 microns, the wave amplitude would reduce to 1 over E of its initial value. The next thing which is asked in this problem, what will be the wavelength of the wave inside this material? And as we know, the wavelength is related to the phase constant of the material. So, we first find out what is the phase constant. Beta, which is square root of pi f mu 0 into sigma, and that if we calculate, we essentially get equal to 8885.5 radians per meter, and therefore, we get the wavelength lambda, which is 2 pi divided by beta is equal to 2 pi divided by this quantity 8885.5 per meter. So, that gives you approximately 0.707 micrometer millimeter. So, at 10 megahertz wave, when it goes in a material which is having a conductivity reasonably large, about 2 into 10 to the power 6 moles per meter, the wavelength becomes as small as 0.7 millimeter. Note, when the same wave goes 10 megahertz into the free space, the wavelength for this is 30 meters. So, in free space, this wave will have a wavelength of 30 meters, whereas when this wave will go into a material which is highly conducting material like this, then its wavelength will reduce to as small as 0.7 millimeter. This conductivity in fact is very close to the conductivity of copper. The copper has a conductivity of 5.6. So, if we take a good conductor, that means in practice what we notionally have good conductors, that is like copper or silver or brass, then the conductivity of those things will be typically in this range, and then the wavelength of the wave will reduce to few millimeters when the wave penetrates this material. Let us take one more problem. Let us say some instant and some location inside a lossy dielectric material, the measured peak electric field of a wave is 10 volts per meter. The material has relative permittivity of 8 and conductivity of 100 mhos per meter. Find the average power density of wave at that location. Also find the power density at a distance of 1 centimeter in the direction of the wave propagation inside the material. The frequency of the wave is given to be 300 megahertz. So, since the electric field is given and the medium properties are given, we can find out what is called the Poynting vector, which gives me the power density at that location. Again, since the medium properties are given, we can find out the propagation constant, and then we can find out what will be the amplitude of the electric field at a distance of 1 centimeter in the direction of wave propagation, and then again we can calculate the Poynting vector at that location. So, the frequency which is given is 300 megahertz. So, in this case omega is equal to 2 pi into 300 into 10 to the power 6 radians per second, and the intrinsic impedance of the medium eta for this, that is equal to square root of j omega mu 0 divided by sigma plus j omega epsilon 0 epsilon r. So, substituting now these values, that the conductivity sigma is 100 ohm mhos per meter and the permittivity is 8, we get here sigma is equal to 100 mhos per meter and epsilon r equal to 8. We get the intrinsic impedance of the medium eta, that is equal to 3.44 plus j 3.44. Once I know the intrinsic impedance of the medium and the electric field, which is 10 volts per meter, then we can find out the average Poynting vector P average, that is equal to mod of E square upon 2, and here the peak electric field is given, which is 10 volts per meter. So, this 2 factor will come because of this RMS power. This is real part of 1 upon eta conjugate. Substituting now for eta from here and the electric field, which is 10 volts per meter, peak amplitude, we get the power density, which is 7.27 watts per meter square. To find now the electric field at a distance of 1 centimeter, we require the propagation constant. So, we get propagation constant gamma, which is alpha plus j beta, and that is equal to square root of j omega mu 0 sigma plus j omega epsilon 0 epsilon r. Again substituting the values for sigma and epsilon r, we get the values which are 343.9 plus j 344.36 per meter. So, the attenuation constant alpha for this would be 343.9 Nepers per meter. So, the power density at 1 centimeter would be P average at 1 centimeter from the initial location, that will be equal to the initial P average which we got e to the power minus 2 alpha into distance which is 0.01, that is 1 centimeter. So, substituting for value of alpha from here, we get the power density at 1 centimeter, that will be equal to 7.49 milliwatts per meter square. So, essentially by systematically following the theory which you have developed for uniform plane wave, we can, using the medium properties, essentially we can find out the electric and magnetic fields or the power density or the state of polarization of the electromagnetic wave. So, these problems essentially give some hand-on experience in using the theory which you have developed for the uniform plane waves.